Morning, Year 12. We're now going to take a look at a very, very important reaction, which is nucleophilic addition-elimination. So this is another new mechanism, but it very strongly links with the nucleophilic addition that we've seen, but then diverges sort of halfway through. So in nucleophilic addition-elimination, we're also going to be reacting with a carbonyl compound. So we're going to take our carbonyl group. And previously we looked at either aldehydes or ketones, and we did nucleophilic addition onto them. So we had either a hydrogen or another R group, another carbon chain on there. But in this reaction, nucleophilic addition elimination, we have a leaving group, which I'm going to denote with an L, and we'll see some examples of what those leaving groups can be. But a leaving group this is something that will quite happily take some electrons and leave. So you can break this bond, give it some electrons, and it will happily go away. So they're going to tend to be quite electronegative things. So let's have a look at the mechanism. So I'm gonna do this in sort of a general format. So I'm not going to use any specific chemicals. So I've got my nucleophile here. So I've got a nucleophile. Lone pair on that negatively charged nucleophile is going to attack the carbon, just like it did with nucleophilic addition. Now that carbon, if it's going to accept those electrons, that will give it 5 bonds, so it's got to release some electrons at the same time. And it's going to, just like in nucleophilic addition, we're going to break the double bond and put 1 pair of electrons up onto the oxygen. So that gets us to here. So we've got this thing. Now, in nucleophilic addition, we sort of just stopped here. However, we didn't have a leaving group. We had like another R group or a hydrogen here. And we stopped at this point here with the O negative. We then add an acid in, a source of H plus, and form the OH group there. However, in this, we can return the lone pair back in to form a double bond. And because we've got this group here that will quite happily just go away and take the electrons with it, when this comes back down to reform the double bond, sort of doing the reverse of what we did here, we can then kick out that leaving group. And so we form this back here. So we've reformed the carbonyl double bond. And we've essentially we've just substituted the L, the leaving group, for our nucleophile. So in a sense, it's a form of substitution, but we call it nucleophilic addition elimination because we have an addition step. We add something to it, in our intermediate, and then there's an elimination step. So we eliminate away L, the leaving group, to leave us with our final product. Now the two electrophiles that we're going to cover, at least the 2 classes of electrophile that we're going to see at A level for nucleophilic addition elimination, are the acyl chlorides and the acid anhydrides, which we looked at last lesson. We looked at the nomenclature of those, so we've seen those before. So we've got our acyl chloride and we've got our acid anhydride. Now the reaction is the same, so this mechanism is the same for each of these two. I think some students often just struggle a bit more with the acid anhydride just because it's a slightly bulkier thing that you're drawing in your mechanism, and sometimes struggle to spot where that leaving group is. But they don't lead to any difference in the products. What you will need to know is the pros and cons of using each of them, but we'll run over that after this. So I'm just going to use, we'll do an example reaction using each of these 2 different electrophiles. So the acyl chloride, we'll do ethanoyl chloride. This thing here, and I'm going to choose as my nucleophile, I'm going to choose, we'll use an alcohol, so we'll use methanol. So alcohols are, it's such a powerful electrophile, this thing, that you can use a relatively weak nucleophile in the form of an alcohol. So it doesn't have to be a negatively charged, nucleophile like I used there. So this one here, we've got the lone pair on the oxygen. That's going to attack the carbon-oxygen double bond. Breaks that, puts the electrons up onto there. I'll draw my intermediate. Now, because we this time the nucleophile was neutral rather than negatively charged, which is what I used up at the start of the lesson, we've got this positive charge here. So before we do the elimination step, I'm just going to remove the hydrogen, like so, to form an oxygen neutral. Right, then we can have attack of the lone pair back in, reform the double bond, kick out our leaving group for chlorine. So the chlorine will very happily form chloride, Cl minus, a very stable ion, and the CCl bond is pretty weak, so it's easy to do this. And then this leads to, so we've formed an ester, we've formed methyl ethanoate. So this is a way of getting a very high yield of methyl ethanoate. You could use methanol and ethanoic acid. They're much cheaper than using ethanol chloride, but it's an equilibrium reaction when you use the alcohol and the carboxylic acid, whereas this will go to completion, you'll get a much higher yield. Right, so that's ethanol 1 using an acyl chloride. Then we've got the acid anhydride. So for this one, I will use ethanoic anhydride. That's by far the most commonly used. So this is ethanoic anhydride, and for our nucleophile we'll use some ammonia. So this lone pair, it can attack either of these two carbons here, either of the two carbonyl carbons. They're both chemically the same as each other. So I'll just attack the one on the left. So same process as on this side. So we attack that carbon, break the double bond, put the electrons up onto the oxygen. So drawing my intermediate. So that gets us to here. We've got the positive charge there as well, so we need to remove that. So I should have drawn this a little bit different. I'll put the H there. We'll remove the hydrogen. Right, and then we can have the lone pair attack back in, and this time the leaving group, the thing that will happily take the electrons and go, is this whole thing over here. This is basically a carboxylic acid unit without the hydrogen. We can break that and put that onto there. Oh, I should probably do is add plus Cl minus over there. So for this one, we then form. So we formed a primary amide. And we form the carboxylate ion. So this is called the ethanoate ion. Now, this is not as good a leaving group as the chloride is. It's a slightly a bit stronger bond, the CO bond, than the CCl bond. So it's not as reactive as the acyl chloride, but it's not dangerous to use. It being less reactive makes it safer, and this ends up forming the chloride. You end up forming you're removing an H plus here, and you've got chloride, so you end up forming HCl, which you might normally think of as like a liquid. You think of hydrochloric acid. as this liquid, but actually the HCl is a gas, and if you form too much of it, it's just going to start fuming off as hydrogen chloride gas, which is, I mean, if you breathe that in, it is going to ruin your lungs. Whereas this, again, we've got the H plus from here, and we've got the ethanoate ion, so we're going to form ethanoic acid as a byproduct. Ethanoic acid is a much weaker acid than HCl, so it's safer because of that. It's also far less volatile. So the boiling point for HCl is it's a gas at room temperature. It's somewhere below 20, whereas ethanoic acid is around 80 degrees. So it's far less volatile. You're far less likely to breathe any of it in. So it makes it safer because of that. So just to compare the acyl chloride versus the acid anhydride, as this is a very, very common 1 or 2 mark question that will come up. So if there's any question that requires this reaction mechanism that we just covered, so